Okay, so let's take a look at your review sheet for Unit 1, 3 chapters, Chapter 1, 2, and 3. The first one is the difference between climate and weather. And of course, they both have to do with the condition of the atmosphere, but climate is long-term averages, usually like 30 years or so, and weather is day to day. The next one, Aerosols. I always think of spaghetti sauce, but Aerosols are those, and they're white usually because white would not get hot and absorb extra heat from the sun, but they're like little gizmos out there, usually near airports, that automatically measure things like wind speed, wind direction, temperature, pressure, cloud ceiling, precipitation. So they're called automated surface observing systems. So that's kind of where the raw data comes to make our weather forecasts. You've probably been exposed to in the past the elements of the scientific method. I want you to make sure that you know hypothesis versus theory. Sometimes hypothesis is called kind of a best guess. And then in class, I kind of talked about how hypothesis can be, after lots of experimentation, can be elevated to king to become a theory. The various Earth spheres, when we talked about how they interact with each other, we have there's 4 of them: the geosphere, the atmosphere, the biosphere, and the hydrosphere. So, and yes, they do interact with each other. Kind of the Earth system is composed of these different kind of elements. How is Earth's water distributed? And I just think this is interesting / sad. But far the majority of the water associated with the Earth is tied up in oceans, 97%. 2% in glaciers, and then just the remaining is in streams. So I think the test question is something like, after oceans, where then is the water tied up? And most of the remaining after oceans is in glaciers. Aerosols, we talked about gases in the Earth's atmospheres, but this is in the Earth's atmosphere. But aerosols are suspended solids or liquids in the atmosphere. The relative abundances of gases in the atmosphere. So I would be referring to the permanent gases. So I'm hoping that you know that basically we have most of the gas you breathe is not oxygen, it's mostly nitrogen. About 80% nitrogen, about 20% oxygen. The third, permanent gas would be argon. Variable gases, there are 3 of them. They vary. That would be the water vapor, carbon dioxide in the Earth's atmosphere, and ozone. Speaking of ozone, oh, sorry. See, where did that go? I guess I skipped ozone. I think I hit ozone in the next one. But what you're looking at there has to do with the seasonal swings in carbon dioxide. So remember, there's this famous kind of ongoing experiment since, goodness, was it the 1950s, where in Hawaii they were measuring the CO2 levels. And notice then, I say years, kind of each wiggle, each bump is a year. So there's many years represented here in this kind of extract of that graph. But each little bump actually is the seasonal swing in CO2 due to plant activity. The next one, good ozone. The good ozone is located in the stratosphere, which is the layer above the troposphere. And the good ozone is good because actually it blocks ultraviolet radiation from the sun. The thermal layers of the Earth's atmosphere from the Earth's surface going outward. So the thinnest layer is the troposphere, and you might want to know just a little bit about each one of these, but the troposphere is where the weather is basically confined. Above the troposphere is the stratosphere. Above the stratosphere is the mesosphere. Above the mesosphere is the thermosphere, and that kind of thermosphere, and it kind of peters into outer space. And it kind of alternates as with regard to if you go up in elevation in that layer, what does the temperature do? So in the troposphere, we said it gets in the troposphere it gets cooler. I'll go ahead and add that. No, that's okay. In the stratosphere, it gets warmer, and in the mesosphere, it gets cooler again as you go up. In the thermosphere, technically, it gets warmer again as you go up. Variations in the thickness of the troposphere. Actually, this is one of your homework questions for Chapter 1. your textbook tells us, and we'll be talking more about this, but over the equator, actually, the troposphere is thicker, and it's thicker over the equator because it's nice and toasty there, and thinnest at the poles. Excuse me, the last one there, if we send up weather balloons, we actually get the true environmental lapse rate. But in general, now this is just very general, in the troposphere, for every 1 kilometer you rise, in general, it's going to cool down 6.5 degrees Celsius. Now, again, to get the real environmental lapse rate, you would need to send up a weather balloon to get that. But I'm kind of getting you used to thinking about this environmental lapse rate, how the temperatures change as you go up in the troposphere, and it's abbreviated ELR. So on to chapter 2. So one of the things we talked about was the fact that the angle that the sun makes with the surface actually has a consequence with regard to how much energy is going to ultimately get to the surface. And so I like this figure from a textbook. It's got a flashlight, which would be the sun, straight up and down, so that'd be a 90-degree angle versus a flashlight at a slant. So that at a slant would be like a less than 90-degree angle. And so basically what this is emphasizing is anytime you're anything other than a 90-degree angle, if your sun is less than 90 degrees, then you're going to get what we call beam spreading. And that's like a kind of a dilution of the sun's energy. You're going to want to know these key lines of latitude. There are 2 in the northern hemisphere and their counterparts in the southern hemisphere. The Arctic Circle, the Tropic of Cancer, the Equator, the Tropic of Capricorn, and the Antarctic Circle, and know their degrees. And the next one, which latitudes get the most direct rays throughout the year? So it's called subpolar point up there. But basically, when we're experiencing winter in our hemisphere, of course that's December, the hot spot is going to be in the southern hemisphere, the Tropic of Capricorn, 23.5 degrees. Let's see, 3 months later, we hit one of the equinoxes in March, and hot spot is over the equator. And then we hit the solstice. The summer solstice in the northern hemisphere is June 21st, 22nd. The hot spot is the Tropic of Cancer, 23.5 degrees northern latitude. And then we hit our other equinox, where the hot spot again is back at the equator in September. The next one, the solstices and equinoxes, and when do they occur? So I'm just going to go ahead and kind of take the same chart and write on it. So, of course, December 21st, 22nd in our hemisphere, we call that the winter solstice. March 21st, 22nd, the spring equinox. June 21st, 22nd, the summer solstice. September 22nd, 23rd, the fall equinox. And with regard to what's happening there, of course, our equinoxes in March and September, every latitude has 12 hours of daylight. And then just simply for the winter solstice, I put not much daylight. And for the summer solstice, in June, I put lots of daylight. So couple of terms, perihelion and aphelion. So this little circle I'm drawing actually is the orbit of the Earth about the sun. And it's off-center. The sun is off-center. And so sometimes the Earth is closer, and we call that perihelion. And actually that happens in January. And sometimes the Earth is farther from the sun. We call that aphelion. And that happens in July. The next one, I brought in a figure from your textbook. It's got that person's holding a pan of water and kind of cooking it over an open flame. And 3 ways we can get energy, thermal energy, from one location to another. Radiation, convection, and conduction are all shown here. So basically the kind of the thermal energy oozing out, that's the radiation. And I love radiation because it doesn't need any material to move to get from point A to point B. It just goes. And then we actually have convection being shown in the pan, kind of the blobs of warm water rising, because it's buoyant, less dense, and then cooling off and falling. It makes these what we call convection cells. So radiation and convection are really kind of players in weather, in the Earth's atmosphere energy budget. Conduction, not so much. So conduction would be basically the person holding the handle, and it goes from molecule to molecule to molecule. The next one, basically without touching an object, you can get electromagnetic radiation that object is oozing, and the next two kind of go together. And what you're going to see is that the hotter the object, okay, the shorter the wavelength of the energy it's going to be sending you, and you're going to basically see it at higher intensity. So I brought in a figure from your textbook. You see the hot sun is on the left, and the cool planet is on Earth is on the right there, and actually along the x-axis here we have short wavelength to long wavelength. So not only is the sun got like a peak, you can see it's basically more intense, but it's over to the shorter wavelengths than the Earth. So I kind of made a couple drawings here. Radiation, electromagnetic radiation, will either be transmitted, scattered, or absorbed, and it depends both on which energy. Remember the cousins of electromagnetic radiation, which energy it is, and what sort of particle it's hitting. So, albedo is the fraction of light that will be reflected from an object. Basically, the higher the albedo, the more the reflectivity. Rayleigh scattering is why the skies are blue. So here's a figure from your textbook. Basically, Rayleigh scattering creates those blue skies. It's a type of what we call selective scattering. And it's selective both for that particular, the blue, indigo, and violet from the sun, and it's also selective for the particles, gas particles, nitrogen and oxygen. But I think on your test, probably more importantly, it's gonna, not more importantly, but it's on your test, so it makes it important. This actually, Rayleigh scattering is also why our sunrises and sunsets have those beautiful reds, oranges, and yellows to them. Because basically, when the sun is low on the horizon, it goes through more of the Earth's atmosphere, and the scattering effect is enhanced. So what we get to the observer is basically minus the blue, indigo, and violet. The greenhouse effect, I brought in kind of this last figure, last little box from a figure from your textbook. But basically those things that look like gnats are greenhouse gases. And the greenhouse effect counts on the fact that actually greenhouse gases like carbon dioxide and water vapor, when the Earth oozes long wave radiation, basically redirect that or absorb energy or redirect it back to the Earth, kind of acting as a blanket, the greenhouse effect. Now I added, you need to add reasons for the seasons and types of electromagnetic radiation. They didn't make it to my original review sheet, but they might be on the review sheet you're looking at. So the reasons for the seasons, basically the Earth's tilted axis of rotation is what gives us all sorts of, well, the Earth's tilted axis of rotation is why we have more direct light during parts of the year and not so direct light during other parts of the year. It's also why we have longer days and shorter days when we're different locations as we orbit the sun. So the Earth's actually, remember, the tilted axis is 23.5 degrees. Then the last one here is the types, different forms of electromagnetic radiation: gamma rays, X-rays, ultraviolet, visible, microwaves, and radio waves. And as I've listed them there, that is the shortest to longest wavelength, the most energetic to the least energetic. On to chapter 3. Hopefully you won't need a calculator for this, but be prepared to be able to answer how do you calculate a daily I see now it's the daily range, not the average. So let me add to this. So what you do, I wonder if I meant to say this. I want to make sure I give you the best review here as possible. I think you should be able to, like you see here, calculate the daily average. And there are two ways to do that. You can either take your 24-hourly temperatures and take an average, add them together and divide by 24, or you can take the max and min temperatures, add them together and divide by 2. That's how you get the daily average. Of course, here, and there's definitely a difference between daily average and range. The range is always the max minus the min. So I'm going to go ahead and write that in there. Range is max minus min. So you'll look at your hourly temperatures, you take the maximum, the highest one, and from that you subtract the lowest one. Okay, on to the next one. To calculate for a given location what its annual temperature range is, you need to have the monthly averages. So you'll have basically 12, one for each month. So you'll have 12 monthly averages. And then again, to do a range, it's always the highest temperature. From that, you subtract the lowest temperature. Isotherms, reading a map. So actually, we talked about different isopleths and isotherms connect locations with the same temperature. So you need to be able to interpret a map like this. And so I went ahead and actually the little X, what is it here? You can see it kind of is in the 60s, hopefully. So I kind of put mid-60s. On the map behind it, which is also an isotherm map, you have to look real closely. But if you look in the middle there, it's got contour lines that go, let's see, let me find my mark here, that go, this is actually 40, 30, okay? So this must be between 40 and 50. I put mid-40s there. So specific heat, draw a little picture. Anytime somebody describes the specific heat of a substance, what they've done for that substance is take 1 gram, set it aside, add heat, and they have added heat until it raised its temperature up 1 degree Celsius. Okay, so that's the specific heat of a material. Something that has high specific heat means that you have to add a lot of energy. It's stubborn. You have a lot of energy in order for it to increase 1 degree Celsius. And a good example of that is water. Something with low specific heat means it heats up and cools down pretty easily. Okay. And so an example of something with low specific heat is soil compared to water anyway. Try to see if I can. Okay, so we talked about different effects of surface temperatures of where you live. So for instance, if you live on a coast, we call that a marine location, versus in the middle of land like we do here in Iowa, we call that continental location. So here in orange I wrote water has a moderates the temperature of coastal locations. So that's why if you're on the coast, your annual temperature range is going to be significantly less than if you were an inland location. I put, in other words, i.e. continental winters are colder and our summers are hotter. Ain't that the truth? So the effect of altitude or elevation on a location. So basically, you probably know that as you climb a mountain, it gets colder, and so in general, locations at higher elevations are cooler, and they're cooler due to 2 reasons. One is that going up in the troposphere, temperatures get cooler because we're getting kind of farther away from the Earth's surface. But the other thing is, as the air gets thinner when you go up in elevation, that thinner air does not hold energy from the sun like the thicker air. All right, the northern and the southern hemisphere. So I brought in this figure from your textbook. Basically, the southern hemisphere has a lot more water than the northern hemisphere. So remember, these are figures that you're looking at the poles. The top one's the northern hemisphere, the southern one's the bottom one is the southern hemisphere. So you're looking at the Arctic Circle there, and there is that, at the Antarctic there at the bottom, the southern hemisphere. So one of the things then we said, and I didn't bring this figure in, but that all that large body of water, all that water in the southern hemisphere has the moderating effect to basically make the temperature ranges a lot less than in the northern hemisphere. So annual temperature ranges are less. Smiley face. Ocean currents. So I know this is kind of a hard figure to see. You might want to pull it up in your textbook. But one of the things that's awesome is that we said that the equator actually ends up with a surplus of energy throughout the year. So that surplus of energy actually is transferred poleward by the movement of the oceans. All right. So this is a figure from your textbook that actually the red line is a sunny day and the blue line is a cloudy day. And one of the things we talked about is that the effect of clouds will have a cooling effect during the day and a warming effect at night. So actually then, during a cloudy 24-hour period, assuming nothing else is going on, like an air mass moving in, your range will be a lot smaller. Your daily range will be a lot smaller than if it's a clear day. You're on a clear day, your daytime temperature is going to be significantly hotter, and on a clear evening, you're going to cool down too. So you're going to have cooler minimum temperatures, so your range is significantly more. All right. So this one is annual temperature ranges by latitude, and boy, I know it's really small, but what I did was to go ahead, it's a figure from your textbook, and they look like isotherms, but honestly they mark locations with the same annual range. And so here I have up in the northern hemisphere, okay, I have that locations along that line actually have a temperature swing of 90 degrees Fahrenheit throughout the year. Is that not crazy or what? And if we compare that to the equator, they're running about 5 degrees swing. So near the equator, equator's great for having basically constant energy throughout the year. And we definitely have a swing in energy at the higher latitudes. Absolute zero, otherwise known as 0 K or 0 Kelvin. And absolute zero, all molecular motion stops. So that should get you down the road on the test. The next one has to do with mountains, so I'm going to go ahead and kind of roughly draw our west coast. There's the Pacific Ocean, those are the Rockies, and that's the prevailing wind. We have a westerly prevailing wind. We'll be talking more about that. But the side of the mountain that the wind is blowing on is called the windward side, and the opposite side of the mountain is called the leeward side. The next two go together. Actually, wind chill temperatures and heat indexes are both those feels-like temperatures. Wind chill takes temperature plus wind, and heat index takes temperature plus humidity.